is just another form of the wafer, the type of QC. So let's talk chips with the technical director, Ruslan of ITKey, Ruslan Ivanov. Welcome. Hello, Luzhniki. I always dreamt of saying this. Ruslan? Say again. Just talk to us. Oh, perfect. Okay, so Ruslan, you have the stage. I don't hear you. Hello, dear friends. Today, we'll be talking about microelectronics and what it consists of. What are the main components? What are the nanometers? My name is Ruslan Ivanov. I'm the technical lead for ITKey company. And I'm sure that each and every one of you has at least one gadget, and it consists of chips. And those chips consist of the smallest elements, the transistors. The engineers are trying to push into those chips more and more of those transistors. And there are some laws that say that roughly every 2 years there's twice the amount of transistors in every chip. So to keep the size of the chips the same, not to make them too big with those handles to carry them around, the components become smaller and smaller. So if you have a look to double the amount of chips in the same size, in the same form factor, we need to make them 0.7 times smaller. That's why we will have this number all over the presentation. Why would you need to double the amount of transistors? It's about money. When we talk about the microelectronics, it's a huge business. It's a lot of investments. And people who invest money, they would want their money to return. So with time, they've developed a spiral where investors would invest money and expect some ROI on that. So to get that ROI, you need more and more transistors per square millimeter. To have more transistors, smarter, faster, next generation gadget, and then investors would reinvest and the story would repeat. So that's the cycle. The chips become smaller and there becomes more and more transistors in one chip. At some point in time, this empirical thing was noticed by Intel's engineer, Gordon Moore, and now this is called Moore's Law. Many of you would hear about it. And the first time he noticed it was about 1960. Since then, this rule has been followed rigorously, and roughly every 2 years, the industry would double the amount of chips for the same surface of the chip, the amount of transistors. So let's talk about those wafers. The wafer is a silicon-made chip. It's a polycrystal silicon plane that is used to put the transistors on it. First question, the bigger the wafer, the better for the money, right? We don't need to do some extra work, just let's make the wafer bigger, right? And in the beginning, the industry was following exactly this rule. And we started from 100 millimeters, then 150, then 200 to 50, and now the size of the wafer is about 200 to 300 millimeters. And most of the chips are made on the factories that work with 300 millimeters wafers. People tried to create a 450 millimeter wafers, but for some reason this factory would not pay for itself, because the complexity of the technology to create them increases. You need to grow bigger crystal of silicon, and this is not economically feasible. That's why most of the wafers are 200 to 300 millimeters. So with the same size of the wafer, the only way to make more transistors is to increase their density, to make them smaller and smaller. Why is it so? The smaller the transistors are, the smaller the chips. The bigger is the amount of working good chips, because some percentage of the chips would not be perfect, would not work perfectly. And for a mature manufacturing process, a good coefficient is 60% of good working chips, and with a new technical process, the number goes down. It's about 40%. Why this is the nanometers size and what is measured by those nanometers? Historically, some elements of the chips would be measured in nanometers, like 0.5 millimeter, 500 nanometers. And when we were doubling the amount of chips, those norms would reduce by 0.7, which is length divided by the area, 150, 180, and up to angstroms. Okay, so if we have a wafer size of a given diameter, how do we make them smaller? Physics tells us that, well, you cannot make the transistor infinitely small, because starting with some size, the quantum effects would create the current that will hinder the transistor from working, so it will not be able to manage the current. What do we do in this situation? How did the engineers solve this? What do they measure when they talk about transistors now? The technological norm, when we talk about the manufacturing, had very physical sense in it. Like 180 nanometers would mean that very specific thing, that the smallest element of the chip, usually it's the transistor, that has metal lines that connect it to the other elements that allow the chip to function. So half of the distance between those lines would be called technical norm, and it's called the pitch. So the technical norm is half of that distance. But in the modern processors, this is not so. Let me explain why. If we look at the chip, if we cut it in half, then we'll see that there's a lot of those metal layers, metal lines. This is Intel Skylake, Intel 7 technology. It has 12 layers of metal. The picture doesn't show the last two. And what is below are the chips. So if you look at the modern processor, there would be no parameters with the same norms as was applied previously. Why so? Because in reality, the transistors cannot be made infinitely small. There are physical limitations. How were they solved? If previously they were making the transistors, flat, now they are actually vertical, and instead of planar, which is in one horizontal plane, they use FinFET technology, so they are vertical. Why do they do it this way? Because if it's flat, the area where all the magic happens is limited by that area. But if you put it vertical, then it's much more efficient. So modern transistors will be very complex, up to 1 nanometer or several nanometers in size. So the norms that the marketologists talk about are nowhere to be seen in the modern tech. Just at some point in time, the engineers decided, probably marketologists decided, the engineers just had to agree that each and every technological process would be would have twice more transistors. So let's consider that it's 0.7 nanometers better than the previous one. And if it was 10 nanometers, then the next one would be 7 nanometers. But in reality, there's no tens and sevens, nothing like this. It's just, an agreement to say this is the generation, nothing more. So modern nanometers, when you see them, it's just a marketing name for the generation of the technology being used. So if Intel says we are using now angstrom-sized processors, it's just a marketing name. Let's look at the real chip. Most of you have mobile phones. Some would have Apple, and the core, the heart of the Apple phone is a processor produced by TSMC in Taiwan, custom-made. It's called 3 nanometer process. TSMC calls it N3B. It has roughly 20 billion transistors, 19.5, and it's roughly 3 billion more than the previous generation of Apple processors. So it's like 16% than A16 Bionic. If you look at the size of this chip, it's roughly 1 square centimeter. And in terms of size, it doesn't differ too much from the previous one, but actually there's more transistors there, but not twice more. So currently, the semiconductor industry tells you that they have less and less nanometers, but actually there's pretty much never a doubling of the number of transistors, because we are approaching the limit of what silicon can allow us, and probably we will soon switch to some new technologies, new possibilities given to us by graphene or some other things like gallium arsenide and other stuff. So this generation of chips was quite successful. The percentage of good working chips was higher than for the previous generation, meaning that the manufacturer earns more money. Less processors is thrown away, and the cost of manufacturing the wafer is roughly constant. So, do you now get it, what the nanometers are? Thank you. Thanks, Ruslan. I hope that our audience now understands better where the science is going. During your whole lecture, I wanted to ask, what is going to happen? You said there are new materials, right? So we will be inventing, and we will be hoping for them to invent more energy-efficient processors, smarter, faster. Do you have any forecast? I'm sure it will work for this generation, and if you are choosing the profession, that's one of the most interesting areas to work. Yeah, you need to learn physics, math, and everything. Ruslan Ivanov, ITKey.